Hello everyone and welcome to this webinar about correlative atom probe tomography and transmission electron microscopy at the CCEM. My name is Ramya Cuduvally and I'm a postdoc here at the CCEM. Today's presentation will be shared between me and my colleague Gabe Arcuri. I'll be speaking to the first half and Gabe will take over for the second. In the summer of last year, we upgraded our atom probe from the Kamika LEAP 4000XHR, which was a reflectron fitted tool, to the 5000XS, which is a straight flight path. So our current tool has a new detector with an improved design that allows a detection efficiency as high as 80%. It also allows faster pulsing, a larger field of view, and overall better uniformity across the entire field of view in terms of the hit density and mass resolving power. There are also some major changes to the acquisition controls and software, and in the following slides, I would like to go over some of these features in detail. There are several instrument design related metrics that are important for atom probe data quality, such as having a good mass resolving power, a large field of view, and high pulse repetition rates. But it is challenging to achieve all of this for any given instrument, and the design essentially ends up being a trade-off between these parameters. Although the reflectron fitted tool that we had earlier does better when it comes to the mass resolving power, our current straight flight path instrument offers a greater detection efficiency, faster pulse repetition rates, and a larger field of view. In the following slides, I'll go over some examples that illustrate these benefits. The improvement in detection efficiency for the 5000 series comes from a superior microchannel plate design as well as an updated hits detection algorithm. The atom probe detection system consists of a delay line position sensitive detector as shown in the schematic on the bottom right, in front of which a microchannel plate or the MCP is placed. The SEM image of the MCP is shown here, and the cross section is shown on the image on the left here. When a field evaporated ion impinges on the microchannel plate, it produces a cascade of electrons, which then travel to the delay line detector behind it. The efficiency of the MCP is determined by its open area. The LEAP 5000 design replaces the cylindrical channels in the MCP that was previously used in the 3000 and 4000 models, with a newer design where the openings of each channel are widened into a conical shape, reducing the dead space between channels where impacting ions do not create any signal. As a result, this increases the detection efficiency of the instrument to about 50% for the reflectron equipped model and 80% for the straight flight path model that we currently have. On the other hand, the updated hits detection algorithm leads to an improvement of the multiple event detection, which can be really important for certain types of materials, especially semiconductors. Here is an example of how the improvement in detection efficiency can help, especially when it comes to dopant characterization and quantification. We measured the same sample on both the instruments, that is the LEAP 4000 XHR and the 5000 XS, and we were interested in determining the dopant profile within this region showed in the figure here. While we weren't able to detect the dopant at all on our older instrument, for a similar volume analyzed on the 5000 XS, we clearly saw the dopant peaks, which are the magenta colored peaks here. And we were also able to successfully calculate its depth profile within the region. The second important benefit of the upgrade is the ability to acquire data faster, and this is related to the maximum pulse repetition rate that is allowed by the instruments, a comparison of which is shown in the table here. Faster acquisition implies access to a larger volume in a shorter time. So for example, for the analysis of a typical volume that is 150 nanometers in diameter and about 500 nanometers in height, this can be completed within a couple of hours on the LEAP 5000, where we can be field evaporating up to 5 million ions per minute in laser mode. This also means that we can get to buried regions of interest faster. An example of this is the buried ferrite martensite grain boundary, which we analyzed on the LEAP 5000. Similarly, we can achieve longer runs within a reasonable time frame for when we want to capture as much of the bulk volume as possible. And this is the case when we want to capture as many precipitates as possible, or if we are analyzing multi-layer specimens where we have several layers that are of interest to us that we would like to capture, but they are spaced apart in Z. On the other hand, because higher pulse repetition rates lets us run at a lower detection rate, since time is then less of a constraint, this means that there is a lower mechanical stress on the specimen because we are using a lower instantaneous field evaporation flux, which ultimately means a higher success rate for our experiments. The third benefit that I want to go over is the improvement to the field of view. An example of the increase in field of view that we can achieve is shown here, where we see that it now becomes possible to capture more crystallographic information on the 5000 straight flight path. So in the 5000 series, the ion optics of the time of flight mass analyzers and the detectors have been redesigned. And it is possible to have a continuously variable ion acceleration. And all of this not only leads to a larger angular field of view, but also ensures that the field of view remains more consistent as the analysis proceeds. These design improvements are also related to why we are able to achieve a uniform illumination of the detector area and a more homogeneous mass resolving power over the full detector area. LEAP is also a lot more user-friendly. A particularly attractive feature that makes sample exchange and user training a lot more simpler and faster is the transfer assist function, which works simply by drag and drop. So this feature allows semi-automated transfer of a puck from the load lock into the buffer, from different positions on the carousel in the buffer chamber, from the buffer to the analysis, and vice versa. There is also an option to have this feature disabled if needed. We also have improvements to the laser and its controls. The laser itself has a smaller spot size, which helps improve data quality. And it is also now much more easier to align the laser to the specimen apex. The adaptive laser scanning and laser focusing control system enables an improved alignment precision as well as accuracy, and this can be more easily maintained throughout data acquisition. The way this is achieved is by building up multiple scans to improve response statistics, more frequent laser repositioning, as well as drift compensation. The time interval for drift compensation can be set by the user, and this is typically set to about 10 minutes. And because we have a higher scan rate as well, we can expect less drift between scans, so it can afford to scan over smaller areas. All of this improves data quality as well as yield. There are a few more really useful features worth discussing, and these are the constant field control, the auto pulse rate control, and the auto pulse energy control. The constant field control is used to automatically adjust the target detection rate to account for the increase in the field of view as analysis progresses. This helps keep the evaporation field constant, which then reduces the electrostatic stress on the specimen and therefore improves the yield. The auto pulse rate control allows the user to collect data faster by continuously varying the pulse rate during the experiment. Since the time of flight depends on the specimen voltage, flight times get shorter as the analysis proceeds. We can use that to our advantage with this feature by allowing the pulse rate to increase as acquisition proceeds. All that is required from the user is the maximum mass to charge state value that we want to detect on the mass spectrum. The auto pulse energy control is another powerful feature that lets you maintain the charge state ratio at a constant value. This means that the laser pulse energy is controlled by the software, and it is adjusted so as to maintain the user specified charge state. This feature can be particularly useful when trying to evaluate repeatability of atom probe results. The last additions that help with a more efficient analysis are the live calibration and live reconstruction features. The new software allows the user to choose certain peaks from the mass spectrum, which it will then use to make the voltage and bold corrections as we are acquiring the data. After it has done this, it can also automatically assign these ranges to the mass spectrum, which saves the user considerable effort. The live reconstruction, on the other hand, allows the user to visualize regions of interest during acquisition so that the experiment can be stopped once we are past the region of interest, such as a grain boundary or an interface. With the instrument upgrade last summer, we also purchased a vacuum and cryo transfer module, or the VCTM, which is a portable suitcase that attaches onto the LEAP 5000XS and the Zeiss crossbeam laser fib and facilitates transfer of samples between these instruments without exposing them to the ambient. It is a cryogenically cooled ultra-high vacuum suitcase which can hold a specially designed thermally insulated puck on it. This add-on expands the capability of APT to air and temperature sensitive materials as well as environmentally unstable materials that could not have been analyzed previously. It can be used for wet biological materials, hydrogen-containing materials, surfaces that may be prone to rapid oxidation, soft materials, battery materials, liquid-solid interfaces, and so on. I'll briefly go over the VCTM operation. The suitcase attaches onto the load lock of the leaf through a coupling that needs to be pumped down before the valves between the suitcase and the load lock are opened. The suitcase is pumped down using a battery-operated ion pump and a non-evaporable getter, and it's cooled to cryogenic temperatures using liquid nitrogen. It always needs to be stored under a vacuum that is in the range of at least E-9 millibar. It uses a transfer rod type mechanism, same as that of the LEAP, to transfer the cryo puck from the suitcase into the LEAP load lock and vice versa, and also from the fib into the suitcase. When attached to the Zeiss crossbeam via the Leica module, a special cryo stage can be used that can hold the entire LEAP puck on it. Currently, we are working on optimizing the VCTM workflow at the CCEM. With this, I will hand over to Gabe, who will talk about the correlative APT TEM workflow. Thank you.
Thanks, Ramya, for the updates on the LEAP 5000. For the next part of the webinar, I want to show some of our improved correlative capabilities here at CCEM that go hand in hand with our APT research. So I'll start with this slide, showing the wide range of instruments at CCEM that allow us to characterize materials from centimeters right down to the atomic scale. For example, we can start on the left with in situ electron microscopy or 3D characterization techniques, such as our new XCT system or EBSD on our PFib, and use these to identify and target unique features. And then we can take our sample and use advanced ion microscopy, such as our new laser fib, to prepare these target features for higher resolution analyses like TEM or atom probe. So having this network of capabilities at our center obviously has its advantages, but it also requires workflows and holders that allow us to transfer our sample from instrument to instrument. And for atom probe, we are particularly interested in the transfer between the fib, where we prepare our samples, and the TEM, where we're able to do high resolution imaging of our specimen. So the reason we want to use electron microscopy together with atom probe is that it provides both structural information, such as crystallography or internal features, as well as chemical information, which can greatly enhance our understanding of the material. So to highlight this, I chose 3 examples shown below, the first 2 being correlative work done here at CCEM. So in the first example, it's human bone, and TEM reveals a very detailed structure. Atom Probe complements this by allowing us to map the chemistry of these features, seen here as alternating mineral and college-enriched bands based on enriched calcium and carbon concentrations. This mapping also shows the co-localization of sodium with organic components, as well as at interfaces. The next example was looking at the corrosion resistance of electrodeposited copper, which is used as a barrier for nuclear used fuel containers, or UFCs. In this work, we were interested in changes in the copper microstructure due to the incorporation of oxygen at grain boundaries, which can act as a precursor to localized corrosion phenomena. As you can imagine, targeting these boundaries in a nanometer-sized tip for atom probe can be quite challenging. So we use something called transmission Kikuchi diffraction, or TKD, which I'll talk about in more detail later, to track the boundary and position it in the apex of the final APT tip. And the final example is some correlative work done by workers from the Max Planck Institute on an aluminum manganese alloy. Here they use dark field TEM and diffraction to confirm a twin region in an APT specimen, and then like with the Bowen example, the atom probe data complements TEM by providing compositional information, in this case to map the segregation of manganese at the twin boundary, as well as a depletion outside of the twinned region. Another area where correlative work is useful is to help with the atom probe reconstruction by providing high-resolution information about the specimen's geometry. For example, this work done by the Curving group overlaid TEM bright field images of different mineral tips before and after atom probe to measure the amount of material analyzed. Then they were able to use this information to define an electric field parameter for 11 different minerals, providing a set of standardized reconstruction parameters that can be utilized by others working with the same materials. Likewise, high-resolution imaging of the tip provides information about the evolution of the specimen during a run and the local magnification effects that influence the data. So for example, this work from PN&L on gold nanoparticles embedded in a magnesium oxide shows how after APT, the gold particles protrude from the surface of the tip, resulting in trajectory overlaps, so the mixing of matrix and core of the particle. And this ultimately affects the chemistry at the interface. So it can be seen by these examples that having this correlative work only aids in the interpretation of the data. However, it doesn't come without its challenges. So for example, we have to take into consideration the complexity of transferring the sample between the fib, the TEM, and the atom probe, which requires careful handling of our extremely fragile tips, usually placed on our sharpened half grid. As well, we have to consider the holders we're going to use, which are compatible with all three instruments. And then finally, we need to consider how the exposure to the energetic electron beam and carbon contamination can affect our specimen yield in the atom probe and the data we collect. So to highlight the challenge of transferring a sample, we can take a look at this image. It's a bent APT needle containing a meteorite sample that was quite difficult to prepare. So after all the fib work was done and TEM imaging was done, the post got bumped upon transfer out of the TEM and couldn't be used for atom probe. So as you can imagine, this is how I felt. So to overcome the challenge of transferring specimen between instruments, we worked with the ultra-fast electron imaging lab at the University of Waterloo to design and manufacture a custom half-grid holder for this correlative work. Where it shines is that it allows for the efficient cycling between our Talos 120 and Talos 200 TEMs, our fibs, and our LEAP without having to touch the half-grid during transfer, which greatly reduces the risk of damaging our sample. It can also hold a range of half-grid sizes from a standard 30 micron copper grid up to custom, thicker 200 micron grids, which I can tell you more about in a bit. But first, I'd like to go over an example of a workflow using this holder. So to start, we need to fabricate something to hold our APT needles that mimics a traditional silicon post coupon. To do this, we can use a fib to sharpen the posts of the TM half grid into a needle shape approximately 2 microns in diameter with a flat top. Here you can see a standard 5-post copper half grid clamped into the top of our custom holder, and this geometry allows for relatively easy loading. And again, once the half grid is inserted, we don't have to touch it again, reducing the risk of bending any posts. Then our correlative holder with the grid can be placed into any 2mm holder and transferred into the fib. In particular, we use our plasma fib as the xenon beam source allows us to efficiently fabricate the posts in a reasonable time. So more on the making of our posts. Once the half grid is placed into the fib, we can begin a series of milling steps to slowly reduce the size of the post, with the final diameter again being about 2 microns. This is what we typically use for an atom probe specimen, but I guess it can be easily adjusted to whatever size post you need. And then this is finished with a roughly flat top cut so that we can place our sample on it later. And many thanks to our fib expert Travis, who you likely recognize from his previous fib webinars, who developed this user-friendly procedure, making it easy for users to fabricate their own posts on an as-needed basis. Now that we have our half grid sharpened, we can begin preparing our APT specimen following standard lift-up procedures. For this example, I've chosen a martensitic steel and want to target a prior austenite grain boundary for APT analysis. Here you can see the lift-out being placed on our flat top post and attached using our deposition, and luckily we can still see our boundary, shown by the red line. Then we perform annular milling to achieve the correct needle-shaped geometry, and as you can see, or in this case barely see, our boundary. And the more we mill, the boundary becomes harder and harder to follow, to the point where we can't see it anymore during low kV sharpening. So how can we position the boundary in our tip apex and confirm it's there? Well, it's the reason we're all here. Bring on the correlative work. For our first correlative technique, we can use our PFib equipped with an Oxford symmetry detector and Aztec software to measure and map the crystallographic orientation and microstructure of our sample with a high spatial resolution, meaning it's ideal for us looking at the grain boundary in our thin APT specimen. To do this, we can modify the more traditional EBSD by instead measuring how the sample diffracts transmitted electrons rather than those reflected off the top surface. This is referred to as transmission Kikuchi diffraction, or TKD, and provides the advantage of removing the 70-degree tilt angle common in EBSD. Instead, as we see in the schematic, we can use the normal 52-degree stage tilt used for milling, which allows us to perform low kV sharpening of our tip and collect a TKD map without changing any geometry, therefore confirming the boundary while easily positioning it in the apex of our tip. So, then why do we need a correlative holder to do this? Well, we need to minimize any reflection of the transmitted beam off nearby surfaces, including the holder itself. For example, when using a traditional silicon coupon and a tilt angle of 52 degrees, we can only do TKD on tips positioned on the edge rows. Whereas the height of our tips on the half grid while using our holder avoids any reflections of the beam. The holder also has a slanted design to allow for a higher tilt angle if needed, such as doing EBSD of a thicker portion of the sample prior to annular milling. So, in the case of our steel sample, we're able to use TKD to confirm our boundary while mapping the misorientation across it and position it within the apex of our tip. Looking at the next stop in our workflow, the TEM serves as another way to look at the structure and crystallography of our specimen with high resolution, either by imaging or through diffraction. The bent post you saw earlier was a result of trying to transfer a sharpened tip from the TEM. Now we have a custom holder, shown here, that fits into both our Talos 120 and Talos 200 TEMs. What makes this arm unique is the custom end form, seen here, that holds the smaller T-shaped holder and half grid. Again, we don't have to touch the grid, just the holder, reducing the risk of breaking the posts we've already worked so hard to make in the fib. And after initial testing, using the 5-post half grids, the x and y stage coordinates of the tips in the TALOS 120 were roughly centered upon loading the holder, making finding the tips relatively easy. Now, what you're probably more interested in is our steel example and what the high-resolution image of our boundary looks like. And there it is, our clear boundary positioned in the apex of the tip. But unlike with TKD, where we're only looking at the diffraction patterns formed from the near exit surface of the specimen, in the TALOS, we can tilt the holder, and the result in our case is that we can see a second boundary normal to the first that was previously not identified. So the next step in our workflow is to use the atom probe to see how these boundaries differ and what elemental segregation may be present for each. And luckily, thanks to our holder, we can directly take these tips right from the TEM and load them directly into the leap. For the leap, we want a holder that is going to be just as easy to load and align as a traditional coupon and clip. Here, we can see the correlative holder and grid fits directly into what we call a puck that then gets placed into the leap. And the holder is sitting approximately the same height as a traditional clip, which is important because we want to make sure the tips are not going to hit anything like the carousel above or the local electrode when inserting the puck into the analysis chamber. And Ramya previously told us about all the new auto features with the Leap 5000 that make moving the sample much easier. So the last thing we want is to be worrying about breaking our tips when moving it around. So the holder passes this test. You will also see that the holder is angled when sitting in the puck. This design is important as it mimics a traditional APT clip and the angle the tips sit relative to the laser. Here we can better see the orientation of the tips in the analysis chamber relative to the local electrode. In the top camera, the tips are roughly horizontal, and this mimics a row on the traditional coupon. In the bottom camera, the tips are roughly vertical. Overall, this orientation makes moving from tip to tip and aligning them to the local electrode a lot easier. So looking to the right, we can see our beautiful APT results with both boundaries highlighted using a carbon isosurface. As expected, we see boron segregation that when combined with the misorientation measured in TKD, allows us to confirm that we correctly targeted our prior austenite boundary. We don't see this boron segregation along our second boundary, as this is likely a boundary between two internal martensite grains. And if you recall, I previously said that we need to consider how exposure to the energetic electron beam and carbon contamination can affect the specimen yield. This will likely be material dependent, but in this case, we were lucky and had good yield without a fracture. In the case of poor yield, extra steps, such as an extra low kV cleaning stage in the fib after imaging, can be used to try to help improve yield. And because our tip didn't fracture, we can move on to post-APT imaging steps in the TEM and take a closer look at our tip. After loading the tip post-APT back into the TALOS, we can take a high-resolution image. And if you think back to my earlier slide, taking a post image of our analyzed tip can help improve the quality of the reconstruction by providing high-resolution information about the tip geometry, such as radius of curvature, shank angle, and dimensions of any feature within our APT specimen. Here, I've overlaid my pre- and post-APT images to measure the final radius of the tip and compare it to the initial radius to better predict the amount of material analyzed. Another interesting thing with taking a post-APT image is that we can see how the laser has interacted with the tip and the degree of asymmetry that may have formed between our shank angles. For example, in the image to the right, we roughly see a steeper shank angle on the laser side of the tip. So getting this extra information is very useful and highlights the benefits of having a correlative holder. But of course, in order to do this, we need our tip to survive the APT acquisition. So, to summarize, this has been an example of a correlative workflow and hopefully shows how the extra information from each technique can aid in the interpretation of our APT results. With this type of example, I would previously need to track the boundary in the fib while sharpening, which you have seen can be quite difficult, often resulting in the final boundary either not close enough to the apex or missed completely. Now, the easy incorporation of correlative techniques into our workflow, like TKD or TEM, can provide invaluable structural information while helping target features of interest during sample prep. And post-APT imaging in the TEM, when possible, can aid in the final APT reconstruction and thus correct interpretation of the final data. And all this is made easier by using our new correlative holder. We are excited to use this type of workflow on more types of projects, and hopefully we'll have a lot of new interesting results soon to share with you in another webinar. So to finish up, there's one last correlative piece that we can add to this workflow that I want to briefly share, and that is using our laser fib. Our Zeiss crossbeam is an SEM fib that is also equipped with a femtosecond laser that allows for fast milling of large volumes. I can't go into too much detail as this is still a work in progress, but we can use the laser to design custom grids of different thicknesses, material, geometry, and the idea is that these custom grids can be made depending on what is needed for a project, and they will fit in our correlative holder. I again want to thank our fib expert Travis, who has been working on making the first of these grids using the laser fib, such as this example of a 200 micron aluminum half grid that is great for loading due to its thickness. And of course, if you want to learn more about the laser fib, make sure to check out his webinar on the CCEM YouTube page. So with that, I'd like to thank everyone for tuning in today, and Ramya and I are always happy to answer questions or requests about correlative APT work here at CCEM. Thank you.
Great, thanks Gabe and Ramya. If anyone has questions, please put them in the Q&A. I guess while that's happening, can either of you comment maybe on types of samples that sort of are ideal for this workflow, if there's ones that maybe wouldn't you think work so good, or if it's good for TEM, then you could do it any material?
Yeah, so I think if you can run it in the TEM and get the data you want, then it should be fine. I think the main things is moving your tip from after imaging it and possibly contaminating it with carbon, or reducing. They've shown that going from TEM to atom probe can reduce the yield. So if your sample's not surviving that transfer and you're not collecting atom probe data, then you have to kind of readjust how you're doing it. So doing steps like maybe sharpening it a little bit more to clean it up, that could help. But yeah, it will be material dependent.